Yes, that's exactly what we've got our eyes set on now. And in fact, I've got my title here refers to multi-messenger astronomy. So the XSX collaboration. Most people who have heard of it know that it's had really spectacular success modeling binary black holes. But we're also interested in other systems. The other two compact binary systems are one, binary neutron stars, and then the other one is black hole neutron star binaries, which is what I'm going to be talking about today. And one of the reasons that we are very interested in these non-vacuum binaries is that you can get more than one kind of signal coming out of them. So here's an example right here of multi-messengers. So in blue, there's a gravitational wave signal that comes from our black hole and neutron star as they in-spiral and plunge. And once the neutron star smears out, you cease having much gravitational wave signal. But at the same time, you get a very hot disk of nuclear matter, and it starts radiating neutrinos like crazy. So now we have another way of looking at the same system, and it's at least it's easier to imagine how a neutrino signal might turn into an electromagnetic signal than how a gravitational wave signal would do that. So we're really interested in the third type of signal. Okay, so as with binary black holes, one of the big motivators behind studying compact object binaries, the late in-spiral and merger, is because they're such fantastic gravitational wave sources. And so, my feeling is that binary neutron stars are probably our safest bet for gravitational wave sources. And black hole neutron star binaries, you worry a bit more about them because, nobody really knows how many there are. But if they are out there, they'll be, and there must be some of them, then they will also, be really great gravity wave sources. And for these non-vacuum binaries, one is really interested in seeing if you can take the gravitational waveform and somehow extract information about the neutron star from it. So here's sort of an illustration of how that might happen. So one of the things that we are not even really sure about is what the neutron star's radius is. And a larger neutron star will be more susceptible to tidal disruption. It will be tidally disrupted by the black hole when it's further away, as opposed to a more compact neutron star will continue to in-spiral closer, and so the gravitational wave signal will continue longer up to higher frequencies before you have tidal disruption. And tidal disruption always basically kills the waveform. So one might hope that if we could see the merger waveform, then we could learn about neutron stars. And the danger here is that this part, which is where most of the information is at very high frequencies where LIGO sensitivity isn't the best. Well, let's say you don't the neutron star's radius doesn't excite you, right? So say it's just a number, right? Now, if you're a nuclear physicist, then that number contains all sorts of exciting things in it, but I'm not. I'm an astrophysicist, so a motive that can excite me as well is I'm interested in these systems because they're a way of building nuclear accretion disks, that is, black holes that are accreting matter at nuclear densities, right? And we know, accretion is this very important process in astrophysics, and we study it in a lot of contexts. And it can be qualitatively very different depending on what the accretion rate is and what the density of the material is. And so we might say, let's consider sort of the extreme case. Let's say that we have a black hole, a stellar mass black hole, and it's accreting solar masses of material per second, and the material is at nuclear densities. It's of course not too, there aren't too many ways that one can think of to make such a system. The two very good ways of doing it seem to be that you take these compact binaries, black hole neutron star, or neutron star, neutron star. If you have a black hole neutron star binary, then you know they're going to get close. The neutron star will get tidally disrupted. Most of the stuff will fall in, but there'll be some material left. The high angular momentum stuff will be in an accretion disk. And for neutron star binaries, simulations seem to lead to similar results, although with an extra step involved. Once again, you have two objects circling each other, giving off gravitational waves. The neutron stars collide, and you make a large, hypermassive rotating object, which eventually collapses to a black hole, and then you're left over with some material in an accretion disk that either comes from the envelope of the neutron star, or for an unequal mass binary, it can be from the tidal tail stuff that's fallen back. And you can easily get a tenth of a solar mass or so of material at these nuclear densities, and this is regarded as a promising setup for making a gamma ray burst. So that's our big astrophysics motivation. So before we start looking at simulations, we should think about what we expect to see. Okay, so what happens when we have these types of massive and extremely dense accretion disks that you get? So another thing that the simulations find, another way that they're pretty extreme, is that they're not only are they incredibly dense, but they're pretty hot too. When you have neutron star merger, you get disks that are 10 MeV or so, and black hole neutron star disks tend to be a little bit cooler. That's right. For binary neutron stars, you had two objects smacked together and shock heat, whereas for the black hole neutron star case, you basically had a star that adiabatically decompressed, and so it stayed cold until basically when stuff came to form the accretion disk, it hit against itself, and you got shock heating that way. But you end up with a few MeV disk nevertheless. And so at these densities and temperatures, the thing is going to be radiating neutrinos like crazy, and photons are totally trapped. So neutrinos are actually the dominant way that these disks can cool, and hence the literature sometimes calls them NDAFs, N for neutrino. And in fact, it can be even crazier than that. In the very inner regions, if you have, for the more massive disks, the neutrinos themselves can become trapped. So in our simulations, we often find disks that have neutrino optical depths of tens or so, at least when they first form. And so there have been some 1D, 2D, and 3D studies of these. They've all led to important insights about how NDAFs behave, and I'm going to summarize some of their results in a second. They're of course all limited in various ways, or else I wouldn't be trying to do my own simulations. Because either they have low dimensionality and make assumptions of perfect stationarity, or some of the or some of the simulations used Newtonian physics, and they all of course also use very approximate ways of treating the neutrino transport. So you've got this really dense stuff, and so it's made mostly out of free nucleons, but it's also got some heavy nuclei mixed in there. You can't assume complete chemical equilibrium, because so basically we had a neutron star. It's in nuclear statistical equilibrium, and it's in beta equilibrium. But then when you decompress it, right? So you had this very deleptonized material. Now you have its density drops by a couple orders of magnitude very quickly, and so now you're out of beta equilibrium. And it turns out that the time scales that we see for you to get back are actually sort of comparable to accretion disk timescales. So on the one hand, you can't just ignore these weak processes whereby the composition is changing. On the other hand, you can't just enforce instantaneous beta equilibrium either, because everything the time scales are comparable. You have to be evolving the disk chemically as you're evolving it dynamically. Okay. So energy extraction mechanisms. So the first one that we've already mentioned is neutrinos. These so simulations, quite robustly tend to find these disks giving off, 10 to the 52 to 10 to the 54 ergs per second when they're first formed. And so, and this is important, dynamically for the disk in that it cools it, it changes its composition, and it also gives us one of the primary means that we can get energy, out from the disk to infinity rather than into the black hole. So most of these neutrinos will just fly away and never be heard from again. We'd have to be very lucky for one of these mergers to go off close enough that we would be able to directly detect the neutrinos. They'd have to be within tens of megaparsecs or so. On the other hand, this energy can be redeposited in an electromagnetically visible way, because something like 1% of it will be redeposited when neutrinos and antineutrinos stream out off of the disk, hit each other, and annihilate. This happens preferentially above on the axis, away from the disk, above and below the black hole, and that's a great place for us to be depositing energy if we want a gamma ray burst, because that's also the very baryon pore region, right? And if you want a GRB, the big challenge is you want to dump a lot of energy into a place where there's very little mass, right? So we're very interested in how much of this energy actually gets dumped and what kind of flows it creates. And neutrinos do other things. They don't just annihilate with each other. They can be absorbed by the nuclear matter, mostly at the neutrino sphere, and that deposits energy and momentum onto the matter, and potentially can drive winds, which could have all sorts of effects too. The second major way of getting energy out is with magnetic fields. And magnetic fields are neat. They're physically important. They make great movies. So important effects are, so first of all, we know to expect, these disks are always, like almost all accretion disks, unstable to the magnetorotational instability. So we expect that's going to, drive turbulence, and it's going and lead to and help drive the accretion. And also, simulations usually find that if you have, that the MRI, turbulence ends up leading to these magnetic structures like this that drive jets. So this picture is from my graduate student who's working on MHD, adding MHD to the spec code. So we're starting out with, we've got an accretion disk around a black hole. We stick a magnetic field in it. Right now all that's happening to it is that it's being wound up by the differential rotation, but we do have sufficient accuracy that we're going to see the MRI as it happens. Right now the simulations are crashing before we can see that, but any day now we're going to be seeing this stuff, and then it's going to start looking like this, right? So this is another group's really impressive work. So this is the Whiskey group. They took a binary neutron star, merged it, the star collapsed to a black hole, and then the magnetic field did its magic. And so this is a great way that you can have energy coming out and potentially create an electromagnetic signal. Okay, another thing that people are just sort of starting to look at is, how am I doing for time? Okay, I'm doing okay. Is that you can have, if we have some of this matter in the, when the neutron star decompresses, gets flung out in the tidal tail, and actually is ejected, becomes unbounded or very weakly bounded, so that it stays away from the black hole and doesn't get eaten, over a time period of seconds. then it'll start having nucleosynthesis go on it, and that would make an electromagnetic signal that one might be able to see. And a neat thing about this signal is it would be fairly isotropic, so unlike gamma ray bursts where we think they're highly beamed and you just have to have them shooting straight at you, one might have, this would be not as bright, but you'd have a better chance of seeing more of them maybe. That is, if at a given, and lastly, here's something that people don't talk about much, but being trained as a relativist, it makes me all excited, is that we have these disks that are 0.1 solar masses, and as I'll show you in a little bit, they can actually get significantly more massive than this. So they have a fair amount of mass in themselves, and they're themselves compact massive objects. So if they become non-axisymmetric and dynamical through some kind of instability, then they might themselves be interesting gravitational wave sources. So there have been several things that people have looked into, and right now one thing that seems very likely to happen from a couple of simulations is, like most thick disks, they are subject to co-rotation instabilities, the Papalouzeau-Pringle instability. This instability doesn't require self-gravity to operate, but self-gravity makes it neater, because once you start getting these whopping big m=1 modes, then they create gravity waves. Right? And so, one can ask, are these gravitational waves observable? And one thing I would really like to study is, are they dynamically important? Do they affect the stability of the accretion disk? Do they affect the accretion flow? And maybe, or even probably, the answer is not much. But it's only for a nuclear disk like this that it's not silly to ask the question, right? All right, so black hole neutron star binaries have a sort of larger parameter space than binary neutron stars, because most neutron stars are pretty similar. So there are three significant parameters that we know are really crucial, for determining what the outcome of a black hole neutron star merger will be. And really, so our sort of simple way of thinking about it is that you will only get an accretion disk, or only get a large accretion disk from one of these mergers if tidal disruption happens at a radius that's, basically when the neutron star is outside the black hole's ISCO. We imagine that if the neutron star disrupts while it's in the process of plunging, then most of the matter is it's just going to go in. The neutron star will fall in like a rock, and that would be gravitational wave-wise very interesting. But if it's nuclear disks that excite you, then or gamma ray bursts, then those aren't the cases that you're really going to want to look at. And so each of these parameters, black hole mass, spin, and the neutron star radius, affect your chances in different ways. For the black hole mass, we know the main thing that black hole mass does is a more massive black hole has an ISCO that's further away. And so one finds, after very quick calculation, that large mass ratios mean that you are bad for disks. There'll always be a sort of a critical mass ratio above which you will reach the ISCO while tidal forces are not strong enough yet. So it tells us that we're going to be very interested in low mass black holes, unless we can find some counteracting other parameter that'll let us make up for this disadvantage. And the one that we can look at, the one that's most promising, is the black hole spin. Right? So the higher black hole spin makes you have a smaller ISCO, which is good for disks. Right? And so the studies of us and others have shown that even if you have a fairly massive black hole, as in mass ratios of 5 to 10 or things like that, it is still possible for you to get a substantial accretion disk if basically if A over M is large, is 0.9 or so, or larger than that. One of the things so a study by Francois Foucard, I, and some others did, we looked at how important it was what the orientation of the black hole spin is. And we found that it basically wasn't very important, in the sense that what really matters isn't the black hole spin, but its component along the orbital plane. Right? So if you have a big black hole spin but it's completely misaligned, then you lose the advantage of the black hole spin, and not much else interesting happens. You get precession of the orbit and precession of the disk, which is kind of neat, but doesn't affect the observables very much, so far as we can see. And lastly, there's the neutron star radius. So bigger stars will disrupt further away, which is good for disks. So we sort of have an interest in what the neutron star equations of state is. Whenever someone publishes a paper that constrains the radius to be small, that makes us sad. And if there's another study, looking at some other way that favors a larger neutron star radius, we hope that is true. Unfortunately, the neutron star radius is independent of our wishes. But that's, and since it's unknown, what we need to do is we need to do simulations with a bunch of different neutron star radii, different assumptions about the equations of state. And so a study that I and Christian and some others did a couple of years ago seemed to indicate that nothing except the compaction, nothing except the radius really mattered much about the equation of state. So so we do small neutron star simulations and big neutron star simulations, but it's the latter that we really love. All right, so let's put all this together and look at the parameter space. So here's a glimpse at the black hole neutron star parameter space. On the horizontal axis, I have the aligned A over M, right, for the black hole. So 0 non-spinning and 1 is extremal, right? And on the vertical axis, we have what fraction of the binary's mass is in the black hole, right? So 0.5 would be an equal mass system, and if we're up at 1, then we're in the black hole test particle limit. It means the neutron star is just a test particle. And there's a line that we can draw that looks like this, that divides the parameter space into disruption inside the ISCO. So these are uninteresting, right? Don't make disks. And disruption outside the ISCO, which is the lower right-hand segment of the parameter space, right? And we see, as you expect, you can get up to higher black hole masses if you keep jacking up the black hole spin as well, up to a point, right? And so the first things that people simulated were in this region, right? The sort of medium black hole spin, or you call it non-extreme black hole spin, and the low black hole mass limit. And the reason we did that was because it's easiest, right? Because it's easier if you have the black hole and neutron star being the same size, fewer scales to resolve. It's also easier if you don't have the singularity almost poking at the horizon, right? And so, but we sort of think that this is the really interesting region of parameter space. So here is the expected black hole mass, neutron star masses. We believe are around this line, at least from population synthesis studies, sort of favor 7 to 1 to 10 to 1 type mass ratios. And this hadn't been done for the first 5 or so years of relativistic black hole neutron star studies. And in fact, the first 7 to 1 mass ratio system appeared in a paper that Francois and I and several others just published a month or so ago. So you see, so here are those two simulations. You see, well actually, yeah, we did 3 of them. We've hit this line now. And so we've pushed it into probably the astrophysically relevant regime. And I would like to keep going if we could. I would think that the really, really extreme case would be disruption inside the ergo region, but that is tough. But I won't consider that we're done with this until we can do that, because who knows? I take that as maybe that's a whole different regime. Okay, so how do we explore the parameter space? Now, at this point, we're not at the point yet where it makes sense to be really trying to cover it. So it's only really now that people are talking about that for the binary black hole problem. Instead, what we like to do is, we're looking for representative cases, where we say, okay, what happens when you have really high black hole spin? Well, let's do a couple cases like that, or let's just do one case like that, and it'll give us some idea. Right? And so for each of these simulations, you usually we start out about 4 or 5 orbits prior to tidal disruption. And so, basically the further out you start, the better it is, in the sense, you have you can get rid of, we expect there to be more physical initial conditions, and we'll have more of a waveform that we can output. On the other hand, it's more expensive to do more orbits, right? And each orbit you go back was slower. It took longer than the orbit before. So it's really expensive to make this number go up, right? And we use the eccentricity reduction procedure that Harold Pfeiffer and others in our group invented, so that basically through an iterative process you end up with an in-spiral trajectory that you hone the initial data to get rid of eccentricity, so you have a low eccentricity in spiral. And then a parameter that I didn't talk much about before, except indirectly through neutron star radius, is what do you do for the equation of state? Right? Now, if we had the real neutron star equation of state, we'd know that, right? But we don't have it, and in fact, we like to say that because it not being known is a reason that these simulations are really interesting, because we want to use gravity waves to constrain the equation of state. But it means that, as far as a numericist is concerned, it's another free parameter that we have to mess with. And so when we are, what we do is we use for these parameter space studies, and not only us but everyone else, is we use gamma equals 2 polotropes. And the reason with a gamma law equation of state, so you can have shock heating. And the reason you do this is because it's much less expensive than a realistic equation of state, and we don't know what the true equation of state is anyway. And on the other hand, you can still tune your polytrope so that you get different neutron star radii, right? So you can still study what we had found in our earlier studies as the primary effect of the equation of state, right? And it's also, it's easier to get high numerical accuracy for gamma equals 2 polytropes. They're sort of the magical equation of state, where the density profile is very well behaved at the surface of the neutron star. The density falls off linearly to 0 near the surface, which makes your surface areas much lower than with any other equation of state that we use. Right? So, by the way, are there any questions so far?
But not gamma equal 2, is it numerically hard to solve, or are you going to be able to go beyond this approximately?
Yeah, I'm going to be talking in a little bit about how we have moved on to using tabulated equations of state, and we don't have the accuracy for those simulations that we have for the polotropes. So you have to sort of ask rougher questions, right? And the reason just is again because of the surface behavior. And unfortunately, the part of the equation of state that we do know, that we're confident in, is the outer layers of the neutron star, where we know it's the pressure is dominated by relativistic electron degeneracy pressure. So it's gamma of almost 4/3, and so you always get this sort of sharp feature near the surface. So it's something that we just need to overcome. We can't hope that the true equation of state won't have it. But we have some ideas, and we think we know how to do this accurately now. this is our code. We use SPEC, the spectral Einstein code, which was invented originally by Mark Scheel, Larry Kidder, and Harold Pfeiffer, and now it has a bunch of people who have added important modules to it, and some of them are here. And SPEC is a very unique code in a sense. It's in some ways the most distinctive of the numerical relativity codes. The thing that makes it really different from all the others is that the way that it solves Einstein's equations. It uses spectral methods instead of high order finite differencing. High but fixed order, we'll say. And so that's how the metric is evolved. On the other hand, we evolve the fluid equations basically the same way that everyone else does. We use high-resolution shock capturing methods on Cartesian grids, with sort of standard reconstruction methods, PPM or fifth-order Wino. And so we have two different grids. One is for the multi-domain spectral code, and the other for the fluid evolution. That's this big box, right? And so each of them has their own numerical techniques that are being used on them, and then the two grids have to communicate by interpolation at every step. And so this setup has some advantages and it has some disadvantages. So for binary black holes, it works beautifully, right? And for matter, I would say that in some ways it's better. In some ways it's a little bit better than the other codes. In some ways it's a little bit worse. So things that it has going for it is I think that we can do in-spirals quite well. Because at least during the in-spiral phase, all of the matter is confined into this small region where the neutron star is. So your fluid grid can just be a little box around the neutron star, and you can have very high resolution in that box. And the rest of the space of the computational domain doesn't have any matter. It's just a vacuum space-time, and it can be evolved using the spectral code and have very high accuracy. Except to the extent that error propagates from this small region where there's the neutron star. And again, and we can crank up the resolution inside the fluid grid for the neutron star and keep that error fairly low too. Unfortunately, as soon as the neutron star tidally disrupts, we lose this advantage because now matter is flung out and it's basically everywhere. And so we have to extend the fluid grid, and then the fact that we don't have adaptive mesh refinement on the fluid grid like some other codes do, becomes a real handicap for us. And another issue is because there's all of this, because we have half of the evolution is spectral, and there's all this communication. We don't scale very well, and so we don't do simulations on more than 70 cores or so, which is whereas other codes use more. Right? In the end, it looks like we're sort of neck and neck right now, us and them. But it's kind of good that that the different codes have complementary strengths and weaknesses. It's encouraging that we get consistent results with each other. Right? So let's take a simulation that came from the non-extreme part of the parameter space. So low mass black holes and low spin black holes. So the things that we were able to do first because they were easiest. Here's an example of one such case. This is, as you can sort of see, one of our misaligned black hole spin simulations. This plane is showing you what the well, let's see, what is that showing you? I don't even remember. Okay, no, that's the initial orbital plane. Yes, and because the neutron star and the black hole spin all precess, by the time the neutron star disrupts, it's tilted, right? And the final disk is tilted. So what do we see when we do one of these simulations? So in fact, the general relativity simulations for all of the binaries in this region of parameter space all look the same. Right? So we always find that tidal disruption happens in one pass. That is, once matter starts flowing off the neutron star and onto the black hole, this continues until there's no more neutron star. This is, and no matter what the equation of state is, and no matter what the mass ratio, this is in distinction to what Newtonian simulations were finding. Newtonian simulations had found that if you have a stiff equation of state, you can get the core surviving for multiple mass transfer events. So this is a case where relativistic gravity has really altered things. Well, it's altered them in a way of making the range of dynamics less interesting in a sense. Whereas before you could have qualitatively different things based on equation of state, in GR has shown that actually qualitatively they all do the same, which is sort of too bad. So you see, once the neutron star becomes tidally disrupted, then you have matter flowing out of inner and outer Lagrange points, and some matter flies out in a tidal tail. So you can sort of see the tail here flinging out, and the tail extends to something like 200 kilometers before it falls back over the course of tens of milliseconds. Also, another difference between the GR simulations and the Newtonian ones is that GR simulations have had a very hard time finding unbounded ejecta. You get tidal tails, matter flings out, but it all falls back, right? Which again is sort of not what we were hoping for, because that takes away one of our potential signals. And so at the end of the day, you end up with an accretion disk, and the accretion disk can be fairly massive, even for mass ratio of 4 or 5, and the lifetime of these disks is something like 100 milliseconds. Usually we only evolve for about 30 milliseconds, but you infer the lifetime from the accretion rate later on at the end of the simulation. And the reason that people don't evolve the whole 100 milliseconds is because it's numerically expensive. No, wait, I didn't mean to say that out loud. The reason we do that is because we don't have all the physics we need, and because we don't have magnetic fields, and we don't have neutrinos, and we know that they're going to be qualitatively important as soon as you get the merger.
Question?
Yes?
You drew attention to the fact that the disk is now tilted with respect to the initial orbital line.
Yeah.
Is it strictly aligned to the total angular momentum?
I don't believe so. No, it's not, and it should be precessing, actually. The only thing, so we actually did a calculation, and we've actually seen this, seen the disk precess, in some of our calculations, but it didn't turn out to be as important as we thought it might be, just because the time scale, the period on which it precesses is usually longer than the accretion time scale. So you basically it's tilted, but the tilt angle doesn't change much before it's all eaten up.
But is more or less the equatorial plane of the star.
So in this case, yeah, we have the misalignment angle was something like 20 or 30 degrees. Of course, we only did. So part of that is that we had this. These were low mass black holes. So if we had. The spin of the black hole has, by accreting a bunch of this matter, it's been brought into, they've been made closer. So it would be one of the things that Francois is doing right now is he's going back and doing some of these misaligned cases where now he has massive black holes, and we can see what sort of misalignments we end up with then. Another interesting thing we found is, so it didn't. We still end up with a, even though you have, the disk is out of the plane and its plane changes with time, we still end up with as big an opening angle, as big a baryon clear region as we had when there was no misalignment and everything was always on the same plane. So let us now push things to a more interesting limit. Let's crank up the black hole spin, right? We could crank it down, but we know that that won't do anything interesting for us. That'll just make our neutron star fall into the black hole like a rock. Let's bring up the spin. So here are 3 different spins. So this is from that same paper, as the images I just showed you. So we took 3 aligned cases. The black hole spin was aligned with the orbital plane, and we just increased A over m. We did 0, 0.5, and 0.9. And here is the total amount of baryonic mass on our grid. That is the total amount that has not fallen into the black hole. Right? So initially, and normalized to the neutron star's mass. So initially, it's just 1. Right? You have all the masses in the neutron star, and it doesn't change. And then when you see these curves dipping down, then that means that accretion has started. And as we were expecting, as the Illinois group had already shown in an earlier paper, increasing the black hole spin, does have the effect of leaving you with more substantial disks. But we decided to push things. They had gone up to A over m of 0.75, and we thought it would be fun to go even higher. We went to A over m of 9. And it's really exciting what happened. You ended up with, at least for 10 milliseconds or so after merger happened, you're left with this massive torus that has 40% of the neutron star's mass that's still surviving, right? So this is a really humongous disk, so much that self-gravity has got to be extremely important, and so the dynamics of this disk could potentially be very interesting. Unfortunately, we didn't follow the evolution far enough to see what interesting things might happen, but that's something that we're doing now, and that we have. A postdoc at Cornell, Jeffrey Lovelace, has decided to take this do an even more extreme case. So same black hole mass as before. Now we take the spin A over m up to 0.97. And so he's done the in-spirals. He's in the process of doing mergers. So he's at about this point right now. And so Jeffrey is mostly a high-spin black hole guy, and so he's really interested in what's going to happen to the black hole horizon when you have a black hole that's nearly extremal and it's accreting this huge amounts of mass. Whereas I'm a bit more of a disk person, and so I'm mostly interested in what's going to happen when we take this this disk that weighs half as much of a neutron star, and we just let it evolve for multiple periods. Right? So it's going to be fun, I think.
Matt,
yes.
I was just curious. It looks like all those lines with different spins all cross at the same point at about 0.5. So I wonder if you would expect that even when you go to extremal spin, it will cross at that point. And
that is by construction. We define the merger time to be when half of the mass has fallen in. So if you start at the same at different separation at the same separation, right? Then the ones with higher black hole spin will take much longer to merge, because of the orbital hang-up. Right? Okay, something else that we can do. We can go to high black hole mass. Well, high is not really high, but it's mass ratios of 1 to 7 now. And so Francois Foucault spent quite a long time, improving the spec code. He and Mark Scheel and Bela Zalagi and some others had to make lots of improvements to the spec code so that we could do these more extreme mass ratios and still have some good accuracy. And we've done it now, and so again, when you go up to massive black holes, basically the only interesting part of the parameter space is if you also have high spin, right? So one of Francois's conclusions was that you need something like A over m of 0.7 if you want to have a disk at all, right? And so the most interesting case that he did was, so we had this 10 solar mass black hole, A over m of 0.9, and we saw that, even though it's an astrophysically interesting mass ratio, we did get a big disk. We got something like 30% of the neutron star is initially outside of the black hole after the core falls in and is sort of orbiting. Now, of course, it's accreting rapidly, so this number goes down all the time. And 70% of the material fell directly into the black hole. And something that's potentially very exciting that he found was that there is a few percent of the mass seemed to actually be on unbounded orbits, being ejected from the system. Right? And remember, this is something that had never been seen in a general relativistic black hole neutron star simulation before.
How long did you evolve?
I would have to check the paper. Yeah, I remember that he had to evolve it for some time. And he evolved it at three resolutions. I expect that it was. Gosh, I wish I would have put some plots with time in it. I expect it was 10, 20 milliseconds that he went. Now, unfortunately, there are very significant uncertainties in the trajectory of this material that's headed out, because when we have to expand our hydrogrid as stuff is being flung out, you get lower and lower resolution, and in fact we eventually have to just let stuff that seems to be on orbits that are taking it very far away, we just have to let it leave the grid. And so, unfortunately, these uncertainties are large enough that we can only say that it looks like there's some ejected mass, and we can't say for sure. So this result may disappear when we're able to resolve tidal tails better. I hope it doesn't, but it may. Right? So this is, and not just in our group, but in all of them. This is really one of the major numerical challenges for evolving these systems is tracking this stuff in the tidal tails that go far away. So that's really something we need to focus on. All right. So lastly, let me talk about our efforts to add back the microphysics. So we've left out a lot when we were doing these parameter space studies, and I've told you why. But we know that, and we think that it's probably good enough to do polotropes or maybe piecewise polotropes if what you're interested in is in spirals and disruptions. If what you're interested in is the disk evolution, though, then even to get it qualitatively right, there's a lot more physics that you need to add back. And so we've made an effort here where we've added back a couple of pieces of physics. So first of all, we've taken what we hope is a realistic equation of state, the tabulated equation of state by Latimer and Swesty. There's actually several variants of it, and we use the moderate one, which has for a neutron star mass of 1.4 solar masses, the radius is a little under 13 kilometers. But this is a hot equation of state. And as is necessary for simulations like this, it doesn't assume beta equilibrium. So the pressure is now a function of three variables. It depends on the density, it depends on the temperature, and it depends on the electron fraction, which is basically related to the number of protons compared to neutrons in the system. And the other thing that we've added back, and we needed a realistic equation of state to do this, is we've added some neutrino cooling and neutrino releptonization or deleptonization effects. Now, neutrino transport is an incredibly difficult problem, and it's something that, it's probably going to be occupying people who simulate these systems for years to come. So we did the simplest thing imaginable. So we're only trying to capture some of these neutrino effects and only to order of magnitude. So we have a so-called leakage scheme, which means that you don't have a neutrino field that you are evolving and having neutrino energy be transported from one region of space to another. Instead, what you do is you just you look at the fluid quantities at every grid point. And depending on what they are, you remove a certain amount of thermal energy and a certain amount of a certain lepton number from that point, and it just disappears. Right? Okay, so now deciding how much energy and lepton number to change is itself something that you can't correctly do unless you were doing real transport. But there are a couple of limits where you know roughly what it would be. So if we were in an optically thin regime, then all you'd have to do would be just take the free emission rates, right? And you wouldn't have to do any transport. On the other hand, if we were in a very optically thick regime, then we could just figure out some sort of diffusive time scale and say that the neutrino energy is being bled out at that rate. So this one already is an order of magnitude type thing, and then we just do some sort of of averaging between them to get something that sort of smoothly goes from one to the other as a function of the optical depth. And the optical depth we have to measure, basically doing line integrals from each of the points on the grid. And the dominant source of neutrinos, we have to include different emission and absorption processes. And the main ones turn out are electron and positron captures onto free nuclei. So let's look at, so we're doing simulations of this right now. In particular, right now we've got some runs going at multiple resolutions, that we hope are going to be the ones that prove that we can have confidence in our results. So here's some preliminary results that we've done, though. So this is again Latimer's thrust T220. This is wrong. The mass ratio is 5, and the spin was 0.9. Right? We want a disk. Okay. We evolved from 30 milliseconds before merger, which means we evolved about 6 orbits before the neutron star gets torn apart. And then after merger happens, we evolve 55 milliseconds of the disk, which is actually quite a few disk periods. Right? And we're more interested in the disk evolution now that we've got we've got the neutrinos. So you can see so here is a snapshot from the late in spiral. We have the black hole, and there's neutron star, different colors of different densities. And here's where we have a strong gravitational wave signal. On the other hand, the neutrino signal is very weak. You just have this signal coming, this emission from the surface of the neutron star where there's anomalous numerical heating. On the other hand, after we've torn apart the star and we've made an accretion disk, the density is much lower. There's no gravity waves. On the other hand, this is a point where the neutrinos have increased, dramatically. So here is another of those rest mass plots that I like what I showed you before, and I've also got the black hole mass shown here. So you see the black hole mass is this red line, and I cut it off right here. That's where we stopped evolving the metric because it had become fairly stationary, and we just and we only evolved the fluid after that. And so the initial mass of the disk is about 0.1 solar masses, a typical number as I've been giving. And the lifetime of the disk is again about 100 milliseconds. Interestingly enough, even as the density as the mass is going down all this time, the maximum density, the density in the equatorial plane at the core of the disk, stays fairly constant at several times 10 to the 11 grams per cubic centimeter. You basically have the disk is getting smaller, but it's contracted. It's getting smaller in size rather than just having while keeping the same density. Right. All right, so here are some profiles of the disk at late times, and so we see the density sort of peaks about 40 kilometers from the black hole and then falls off. And we have a Rayleigh stable angular momentum profile. We have a here's the entropy of the disk. We actually see that it does. So we have the entropy dropping in the as you go out in this very inner region. So that's a region that that might have been convectively unstable, except there's also a very strong shear there. This is again is seen in a lot of simulations. And then after that, in the bulk of the disk, the entropy is rising, as you'd expect. And here's the composition, and you see it actually. We have very deleptonized matter in the high density region, and then it's going. That actually doesn't change a whole lot. And one of the things we are interested in looking at is how axisymmetric the disk is, and it's not. The disk is actually never axisymmetric. So we know that because this disk actually, it's a thick disk. It has a well-defined inner and outer radius, and it has a co-rotation point. Even if for the mode that we see here, even if it did start out axisymmetric, we expect that it would be that this is the sort of thing that would be Papelosi-Pringle and unstable, and we might get a mode. But in fact, it was always non-axisymmetric, and the non-axis symmetry is m equals 1 dominated. So basically you have this big clump here and low density here, and the clump rotates, as one would expect it would. But this is not a supermassive disk, so the gravitational waves aren't huge from it. The thermal evolution, so here's the evolution of the average temperature of our disk. So you see we start out at 0.1 MeV, which is the minimum value of temperature that we're allowed to do in the Latimer-Swesty table, and immediately numerical error takes us up to about 1 MeV. Which sounds hot, but it's actually still very degenerate. So it's not something that we should care about. And the entropy here is much smaller than it's going to be when we have a hot disk. So then at this point we have merger, and so the neutron star is tidally disrupting. So we initially get a big blip up in temperature, and that's because the numerical error is getting worse. This is still not the temperature you believe. And then as the star decompresses, because it's being torn apart, the temperature goes down, and then at this point we start getting shock heating, and we get what we believe is the physical temperature rise. And then we have the sort of slow decrease because of the neutrino emission. And we have checked that we do know that the cooling is entirely due to the neutrino emission. So here on this plot, to the right, I have the neutrino luminosity and the change of thermal energy with respect to time in the disk. And you see after we go through this strong accretion phase where there's a lot of matter, heat being accreted into the black hole, they line up very well. So this is a very efficiently radiating accretion disk, and nearly all of the thermal energy does get out, and none of it is being accreted into the black hole. And so as time goes on, like I said, the disk is getting smaller, so the maximum optical depth for electron neutrinos, is what I'm plotting here, goes down, and by the time we get to the end of the simulation, the disk is on the verge of being optically thin. Right, so now we have neutrinos the disks become much cooler, but what thermal energy there is left can just stream out from the neutrinos coming off at the free emission rate. We've also looked at how the composition of the disk evolves in time, and so here's the in-spiral phase. This is the average electron fraction, and during the in-spiral, of course, it doesn't change. You just have a neutron star that's getting closer to the black hole, but it's not doing anything. It tidally disrupts, and so now it goes to much lower densities. So you'd sort of expect that it would re-leptonize, that we're going to have, neutrons are going to start turning into protons. We're not going to have this extremely neutron-dense nuclear matter anymore, because we're not a neutron star anymore. And that is what happens for the early evolution of the disk. And then something unexpected happens. It seems to turn around, and we de-leptonize again. We re-de-leptonize, and then bottom out, sort of closer to where we started. And you can see what has caused that to happen here on this plot to the right. So here we have the emission rate of different species of neutrinos, right? So this green line that's below the others are the heavy neutrinos, the mu and tau neutrinos. On the other hand, the black line is electron neutrinos. The red line is electron antineutrinos. And so initially we get, the red line is above the black line. We're giving off more antineutrinos than neutrinos, which is what you expect from a de-leptonized thing where there's more neutrons to capture antineutrinos. Right? But then at a certain point here, about 15 milliseconds or so after, the point where we have this turnaround here, they switch. And so now we're giving off more neutrinos. And the reason for this seems to be that this is the neutrons that the disk cools fairly quickly. And remember, it's a black hole neutron star disk. It starts out cooler than the neutron star disks that have been more often studied in the literature. And so the electrons are actually are becoming more degenerate. So this is plotted here on this plot is the luminosity average electron chemical potential divided by temperature, and it goes up, and so we end up with more degenerate electrons, and so you have basically more electrons compared to positrons in the region that's giving off luminosity, and so that's why it's easier to give off electron neutrinos. So, is this a new effect, or is this something that's going to go away when we increase accuracy? Well, we'll see. Stuff that we have going on right now, we'd like to look at the neutrino-antineutrino energy deposition, and that is just an integral, right? At a given point, you need the distribution function of neutrinos and antineutrinos, and you need a cross section and how fast they're slamming into each other and what their energy is, and you do this integral over the momentum space of each of the two particles. The tough part about this calculation is you need these distribution functions, and of course we don't have them. The way you get them is you would do neutrino transport, but we can sort of we can approximately infer them doing ray tracing, right? The neutrinos roughly travel on null geodesics. You start at your point where you're interested in, and you trace geodesics backwards until you get to the disk, to the neutrino sphere of the disk, and then you can there are ways that you can infer what the distribution function is. So let's see, and I probably should go fast. All right. So, and then the other thing that I've already mentioned that we're doing is we're doing adding magnetohydrodynamics to the spec code. This is a project that's being led by a couple of graduate students and overseen by me and Francois Foucart. And so as soon as we get this code working, we're going to be confronted by the same sorts of problems that other groups are bedeviled with who have MHD, and that's resolving the magnetorotational instability, which can have a wavelength much smaller than the size of your problem, and unless you jack up the magnetic field to crazy levels, and allowing and getting making sure your atmosphere doesn't completely baryon load, the outflows that you want to see. Okay, so things that are going to be to look for in the future, we want to push the high spin and high mass ratio limit, because like I said, I think that's the most interesting part of parameter space. Numerically, the thing that needs to be pushed is following outflows, meaning following out to long distance, and they're going to have to be evolved for long times, right? And at some point we'll want to add, nuclear physics into these, just so that we can actually see, when and how nucleosynthesis happens. And then, a major issue for everyone who's studying gamma ray bursts is tracking down the energy extraction mechanism, and we have, all these, several things that one has to, look at and see how they come into play and how they interact with each other. So that's all I had to say. Thank you.
The longer time evolution of the disk, do you need GR or can you do this with film?
So we need GR in the sense that the disk is very close to a black hole. So on the other hand, we don't think that we need, depending on the mass of the disk, we don't think that we need dynamical GRs, and you can just take the metric and leave it as fixed. And so that is something that we do after 10 milliseconds or so. We switch. We just freeze the metric, which is these are low. The matter that's left isn't a whole lot, so it's to within 1% or so. It's a Kerr spacetime, but a Kerr spacetime in a coordinate system that we have no idea what it is, because it's whatever the numerical relativity simulation has evolved it to. Right? So it's easy to just leave it where the metric as it is.
Does that mean that you don't have self-gravitation anymore?
So yes, well actually what it means is that the self-gravity of the disk as it was when you stopped evolving the metric is just going to be frozen in there for all time. So if self-gravity is important, then you better not do this, right? Because you would miss all sorts of things,
Well, I'm looking around the room for Tony. You here? So he has these ideas of at later times, like seconds, the clumping of the large amount of material in the disk can lead to little late spirals.
Yeah, so I think
Actually,
so we
collapse artists.
Yeah.
Collapse artists.
Now, is there enough? Okay, yeah. So that's true, and you're not going to see that if you don't have self-gravity. So.
Early on, you showed the sort of mass spin plane and had a dividing line between follow the neutron star hole versus actually a jet.
Yes, I'm proud of this plot. Let's go back to it.
Okay. Do you have an equation for that line, or is it just sort of?
Yeah, there's an equation for that line. I don't know if it's going to improve its credibility if I tell you what it is. Okay, so where that came from was, so I looked up. There's a paper, from the 70s or so by was it Bardeen maybe, where they had the tidal force for a geodesic in circular orbit around a Kerr black hole, and then you set tidal forces equal to the Newtonian self-gravity force for the neutron star up to a constant of order unity, and I use that constant to shift the line so that the numerical data falls in the right places. The ones where we don't see disks and the ones where we do see disks agree with the line. So the line is certainly not exact, but since the purpose of that plot was to be illustrative, I thought it was sufficiently well motivated for that purpose.
All right, let's thank Matt again.